Next up, we have an introduction to series, which is section 11.2. Now, a series is a little bit more complicated than a sequence. The series is an expression of the form a1 plus a2, etc., which is an infinite sum of terms. So, frankly speaking, a series is the sum of the terms of a sequence. Now, it's very easy for a sum of infinite things to be infinite, but it's also possible for a sum of infinitely many things to be finite. So we are very concerned with whether a series converges or diverges. And we have a very easy definition for that. The nth partial sum S sub n is simply the sum from I equals 1. Oh, I used the wrong letter in my first one. We need to make sure that these match all the time. A sub I up to n. So this is just like doing Riemann sums, except now we've got more general things. So the nth partial sum is going to be the sum of the first n many terms, or the sum up to term n, in case your sum starts somewhere other than 1. So in that sense, S sub 1 would be equal to A1, and S sub 2 would be A1 plus A2, and it gets very repetitive. Now, a series is going to be convergent if and only if the sequence of partial sums converges. So a series converges if the sequence of partial sum converges. And this is practically by definition, because the limit of the sequence of partial sums, as n goes to infinity, of S sub n, this is equal to the limit, as n goes to infinity, of the sum from I equals 1 of A sub 1 I up to n. But this should be equal to the sum from I equals 1 A sub I up to infinity, practically by definition. So if a number exists for the limit of the partial sums, then a number will exist for the full infinite series. So if limit of S sub n as n goes to infinity diverges, so must the infinite series. And there's all kinds of neat things we can do with series. Take, for example, our pi example from before. If I add up all of the digits of pi, well, I'm going to be adding up a bunch of random numbers from 0 to 9, and so I'm actually going to eventually get infinity. However, if we look at decimal representations of real numbers, then I really just have to look at the digit and the number which is in it. Because this is the sum, this is equal to 3 plus 1 over 10 plus 4 over 100 plus 1 over 1,000 plus etc. Right? So we can actually do something with this for converting infinite decimals to rational numbers when it's allowed. So a real number r is rational if and only if its decimal expansion or decimal representation is finite or repeating. So if I wanted to, for example, to look at the number 0.2 followed by repeating 3's, then if I think about it, this is actually equal to 0.2 plus 3 over 100 plus 3 over 1,000 plus 3 over 10,000, etc. Or I could say this is equal to 0.2 plus the sum from I equals 1 to infinity of 3 divided by 10 to the I plus 1. This is of course equal to 0.2 plus, out of a sum, I can factor out a 3. I can also factor out one extra 10, so I could write this as 3 over 10 times the sum from I equals 1 to infinity of 1 over 10 to the I. But this type of sum right here is actually a very special sum because we might recognize this from the last section, that 1 over 10 to the I as a sequence is a geometric sequence. So the sum from I equals 1 to infinity, 1 over 10 to the I, is a geometric sum. And what we'd like to do is know whether or not it converges. So let's consider this. The sum from I equals 1 to infinity of 1 over 10 to the I is equal to 1 over 10 plus 1 over 100 plus 1 over 1,000 plus ... which I could write as 1 over 10 plus 1 over 10 times 1 over 10 plus 1 over 100 plus ... which is equal to 1 over 10 plus, what do we got here? 1 over 10 times the sum from I equals 1 up to infinity of 1 over 10 to the I, because these are infinite. So if this actually converged, I suppose I don't actually know whether or not it does converge, but if I know that it does converge, so if we know that the sum from I equals 1 to infinity of 1 over 10 to the I is finite, then we know that the sum from I equals 1 to infinity of 1 over 10 to the I is equal to, its bottom line, 1 over 10 plus 1 over 10 times the sum from I equals 1 to infinity of 1 over 10 to the I. And I could just subtract that over to the other side, giving me 9 over 10, 1 over 10 to the I, equal to 1 over 10. Or I get 9, which is pretty neat. So let's try to find out more about these geometric series in general. So we'll consider a general one, I equals 1 up to infinity of a times r to the I. Then its partial sums, s sub n, is equal to, well, it's the sum from I equals 1 up to infinity of a times r to the I, no, not infinity, n, which is equal to ar plus ar squared plus ar cubed plus dot 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 up to ar to the n. But this is equal to, I can factor out an a, and I can factor out an r, leaving me with 1 plus ar plus r squared plus r cubed plus dot 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 all the way up to r to the n minus 1 because I factored out an r. Now, in fact, if I multiplied and divided by 1 minus r, and I encourage you to check me on this, ar times this big guy multiplied by 1 minus r and divided by 1 minus r. I can multiply and divide by things, that's okay. So I should note that r should not be equal to 1. Which makes sense, because if r is equal to 1, then I'm going to be adding up infinitely many copies of a. So I'll have infinity times a. That's bad. Definitely diverges. Well, it turns out when you multiply this product on the top, ar, we end up with 1 minus r to the n, all divided by 1 minus r. So what I would like to do, I have a nice little formula here for the nth partial sum, is I would like to find out what the limit as n goes to infinity of s sub n is. Because this is the definition for the infinite series sum, is the limit of the partial sums. So this is ar times 1 minus r to the n all over 1 minus r, which I guess I could distribute this top to get ar over 1 minus r minus ar to the n plus 1 divided by 1 minus r. Now, ar over 1 minus r, that doesn't contain any n's, so this is equal to ar over 1 minus r minus the limit as n goes to infinity of ar to the n plus 1 over 1 minus r. But again, the a and the r don't depend on the n, so I have a over 1 minus r multiplied by the limit as n goes to infinity of r to the power of n plus 1. But you'll recognize this. We did this in the last video. This limit right here, this is the limit of a geometric sequence. And we said last time that this is convergent. So if r is equal to 1, it converges to 1. If r is greater than 1, it diverges. And if r is less than 1, I should have absolute values here. Then if r is greater than 1, no, if r is less than 1, then it converges to 0. I'm already out of luck in the r equals 1 case because I've observed that if r is equal to 1, then my geometric series is just going to be an infinite sum of a. I'll have a times infinity. So unless a is equal to 0 and I just have a 0 sequence, I'm going to have an infinite sum, or a divergent sum. Which means the sum from I equals 1 up to infinity of ar to the n diverges if r, the absolute value of r, is greater than or equal to 1, and it converges if r, the absolute value of r, is less than 1. But specifically, we found out what this limit was. It was exactly this, ar times 1 minus r. Did I say times 1 minus r? I don't even know. In general, this might disagree slightly with the book. Some books start with I equals 0. Some books will start with I equals 1. Some books will change the power to n minus 1. Some books will change the power to n plus 1. They just all do kind of different things. But in general, if you recognize a geometric series then the sum from I equals any number, really. We'll say I equals m to n of a times r to the n, no, I. This will be equal to the first term divided by 1 minus r. And the first term in this case is going to be ar to the m. If I started my sum at 0, I would have exactly a over 1 minus r. So up here, when I wanted a rational number, well, I've already proven that this number, sum of 1 over 10 to the I, is equal to 9, because this work combined with the facts down below says that this number must be 9. But specifically, right here, this is equal to 0.2 plus 3 over 10 times 9. But that's equal to, let's see, that's 2 over 10 plus 27 over 10, which is equal to 29 divided by 10. That's not right. Let me try to find out what I did wrong there. If that product is equal to 1 over 10, oh, I see what happened. I went a little bit too fast. I should have gotten the sum of I equals 1 up to infinity of 1 over 10 to the I is equal to 1 over 10 times 10 over 9. I should have gotten 1 over 9. If I had just followed the formula I got down below, I would have had the right answer, because the sum from I equals 1 up to 10 of 1 over, nope, to infinity of 1 over 10 to the I should be equal to 1 over 10 divided by 1 minus 1 over 10, which is 1 over 10 divided by 9 over 10, which is 1 over 9. There's multiple ways to derive the formula, but you need to verify that the series is actually going to converge first. So it looks like I screwed this up completely. I should have 0.2 plus 3 over 10 multiplied by 1 over 9, which is 2 over 10 plus 1 over 30, which is, of course, 6 7 divided by 30. And that, you can go ahead and check with the calculator. So we'll remember this one. Oh, I suppose I should have this as well. And it's true for whatever you want to have. So actually a popular question that has ended up on some of the tests, the sum I equals 1 up to infinity of e divided by pi to the I. They're not even whole numbers, but e is approximately 2.7182818280459, and pi, well, you know how much I know about pi. So this should be equal to, well, so e over pi is certainly less than 1. That's great. Which means that this sum, I equals 1 up to infinity of e divided by pi to the I, should be equal to, first term, e over pi divided by 1 minus r, which is e over pi. This looks like e over pi divided by pi minus e. But if I remove e from pi, don't I get pi again? So I end up with e over pi minus e. Now it's possible we might try to hide the geometric series a little bit by adding in some distracting information. Like I might have the sum from I equals 2 up to infinity of 14 times the square root of 2 to the n multiplied by 1 over 3 to the n minus 4. This is still a geometric series, but we have to work on it a bit in order to see it pop out. So the main goal is, well, the first thing I should recognize is there's an r to the n. Oh, I used the letter n. Let me change my index to match. I should be more careful. I have an n in the exponent, and the n here is my index. So this tells me I'm probably going to have a geometric sequence, or series. So I should try to rewrite my summands so that I have a single r to a single n. So I'll leave the 14 sitting out here. I'll leave the square root of 2 sitting right here. But this 1 over 3 to the n minus 4 is the same thing as 1 over 3 to the n divided by 1 over 3 to the 4. Subtraction among the exponents is the same thing as division among the bases. So I can combine these two guys. I'll leave my 14 and 1 over 3 to the 4th off to the side. But this is negative, so this is 14 times, this number here is 81, multiplied by, let's see, I have root 2 to the n times 1/3 to the n. So I have the same exponent there, so I can combine these. 14 times 81, whatever that is, multiplied by, let's see, I'll have the square root of 2 divided by 3 to the power of n. So I have some number sitting out here in the front, and I have some r to the n. R equals root 2 divided by 3. So the question is, does this series converge? Well, the answer is yes, because the square root of 2 is obviously less than 2, so this is less than, this r is less than 1. So let me just say, yes, it must converge to the first term is 14 times 81 times the square root of 2 divided by 3, quantity, the first term starts at n equals 2, divided by 1 minus the square root of 2 over 3. And I could try to simplify that, but it's already equal to the correct answer, so I'm just going to leave it just like that. But it's interesting, because if I had taken the same problem and I flipped the r, or perhaps if I took the previous problem and I flipped the r, if I had pi over e, the sum from n equals 1 up to infinity of pi divided by e, this would be infinite, since pi over e is greater than 1. Now I can't help but notice, though, that all of these series, or the convergence of these series, pretty much exactly coincided with the fact that the terms of the inside went to 0. Because the only exception was when r was equal to 1. So maybe the requirement is that the terms go to 0. And in fact, that makes plenty of sense, because if the limit of the terms is not 0, then eventually my series is going to be approximately equal to an infinite number of copies of that limit. And I say theorem, but this is actually a test for divergence. If the sum I equals 1, or if the sum from n equals 1 to infinity of a sub n converges, then the limit as n goes to infinity of the sequence of the terms a sub n must be equal to 0. And this makes sense, because if I have an infinite sum of things, then most of these things should be practically 0. Or they should eventually go to 0 at the end of infinity, because if I'm adding up infinitely many things just to get a single piece, they better be tiny. So conversely, if the limit of n as n goes to infinity of a sub n is not equal to 0, then the sum must diverge. Actually, it could be positive or negative. But notice that this doesn't say have any condition for convergence of the series. I require the series to converge to declare that the limit of the terms must go to 0. If the limit of the terms does not go to 0, then my series must diverge. But it is not true that the limit of the terms going to 0 is enough to say that the series converges. And there is a standard example that everybody should remember for the rest of their lives. The sum I equals 1 up to n of 1 over n, the harmonic series, diverges. And we learned this in the next section after this test, technically. It's from the integral test. But this is a divergent series. It grows very, very slowly, but it does eventually get infinite. But the terms clearly go to 0. And there are worse examples of this, but we'll get to more of those afterwards. But it does say that if my limit is not 0, then I have a very clear indication that my series is going to be divergent. So if I have the sum from I equals 1 up to infinity of, let's say, n squared minus 1 over 17n squared plus 47. So here I have a sub n equal to n squared minus 1 over 17n squared plus 47. And the limit of a sub n goes to infinity, a sub n is equal to the limit as n goes to infinity of n squared minus 1 over 17n squared plus 47. But this is actually a rational function of polynomials. If I translate this into x's, then I suddenly have a bunch of things I could do to try to resolve this limit. Specifically, I could just look at the coefficients. I could use L'Hopital's rule twice, or I could use the methods of section 2.6, divide the top and bottom by 1 over x squared. Either way, I'm going to end up with 1 over 17 as my limit, which is not equal to 0. So by the test for divergence, this must diverge. And we can probably check this with a calculator, but since this limit is 1 over 17, that means after maybe a couple 100,000 terms, I'm approximately adding 1 over 17 infinitely many times. And infinity times 1 over 17, or infinity divided by 17, well, that's just infinity again. So before we move on to our last class of examples, we're going to talk about some properties of series, which is exactly properties of sums. We've allegedly talked about this in the previous class. Although there are some properties which hold for finite sums which will not hold for infinite sums. So one, I've already used this one. Sum from n equals 1 to infinity of c times a sub n. This is equal to c times the sum n equals 1 to infinity of a sub n. This is essentially a sum of things, and if I have a common factor among a sum of things, no matter if it's infinite, I can factor all of those out. The sum from n equals 1 to infinity of a sub n plus b sub n is equal to the sum from n equals 1 to infinity of a sub n plus the sum n equals 1 to infinity of b sub n. And what works for addition must work for subtraction. However, sum n equals 1 to infinity of a sub n and the sum from n equals 1 to infinity of b sub n must converge. Because if they diverged, well, I could end up with infinity minus infinity indeterminate form when I split up these sums. And that's bad. There's technically another one, which we probably won't make use of. Sum from n equals 1 to infinity of a sub n is equal to the sum from n equals 1 to infinity of a sub sigma of n if a sub n is greater than 0 for all n. And this means scramble the entries. So I can rearrange the terms of my series as much as I want if the terms are all positive, or mostly positive. If I have only finitely many negative entries, then I can kind of shove those off to the side. But as long as they're all positive, I can rearrange them. Or if they're all negative, I could rearrange them. But if they're half positive, half negative, if they kind of alternate, then I can't legally rearrange them because that might screw up the value of the sum, because weird things happen when you include infinity. The fourth property is a splitting property. This is equal to sum n equals 1 up to m of a sub n plus the sum n equals m plus 1 up to infinity. I can chop off however much I want of my sum and still have a coherent expression. So if particular value is property 2, because that says we can combine or separate series if we need to perform different kinds of tests on them. We don't have very many tests right now, but in the future we'll have quite an array of tests for convergence and divergence for series, and so we might have a series of an expression that could require more than one test in order to determine its convergence. And so we'll separate the sum. We'll do one test on the first part and a different test on the second part, just like in integration where we might split the integral to do one technique for the first part and a totally different technique for the second part. So our last kind of example, or last type of basic series, is the telescopic series. It's so-called telescoping because it collapses on itself. I have terms which cancel each other. In a telescoping series, well, I don't think I can adequately define a telescoping series in general. So why don't I just do one with an example. We'll do the sum from I equals 1 up to infinity of 1 over n plus 1 over n minus 3. No, wrong direction. Minus 1 over n plus 3. So I should add as a note here, some of these may require partial fraction decomposition. But what I should observe here is that a part of the terms of my series can be expressed by some sequence which has a future or later term reappearing in my expression. So I have a 1 over n here and a 1 over n plus 3. Well, 3 terms later, I'm going to be on 1 over n plus 3, but also 1 over n plus 6. So the way I handle this is I can't split it, because based on what I've given here, I have the sum of 1 over n, which I just said diverges. So I can't split this into two sums and try to evaluate that way, because I would have infinity minus infinity, which is indeterminate. So instead, the only other option I have is to try to find the limit of the partial sums. But in order to do that, I would have to find out what a partial sum looks like. So let's try to make some partial sums. S sub 1 equals 1 over 1 minus 1 over 4. Great. S sub 2 equals 1 over 1 minus 1 over 4 plus 1 over 2 minus 1 over 5. S sub 4 equals 1 over 1 minus 1 over 4 plus 1 over 2 minus 1 over 5 plus 1 over 3 minus 1 over 6 plus 1 over 4 minus 1 over 7. But here we see stuff starts to cancel. And if I do another term, I'll start with 1 over 5 and I'll cancel this one. If I do another term, I'll start with 1 over 6, and I'll cancel this term. So let me jump ahead to S sub 6. I'll have 1 over 1 minus 1 over 4, 1 over 2 minus 1 over 5, 1 over 3 minus 1 over 6, 1 over 4 minus 1 over 7, 1 over 5 minus 1 over 8, and 1 over 6 minus 1 over 9. 1, 2, 3, 4, 5, 6. Okay, perfect. 1 over 6 is canceled, 1 over 5 is canceled, and the 1 over 4 is canceled. So what does this imply a general term is going to look like? If I included one more term, I would have canceled the 1 over 7. That would have completely gotten rid of this term entirely. So it seems like every term after the first three will eventually get completely canceled off. However, I'm always left with these last three terms. So you can check me on this by doing s sub 7, 8, and 9. But what you should find is that s sub n can be described using, let's say I'm left with 1 plus 1/2 plus 1/3 minus, this was 6, 1 over n plus 1 minus 1 over n plus 2 minus 1 over n plus 3. But the limit, as n goes to infinity, of s sub n, this is actually equal to, well, this goes to 0, this goes to 0, this goes to 0. This is just equal to 1 plus 1/2 plus 1/3. Which, with a common denominator of 6, is 6 plus 3 plus 2 divided by 6, which is 11 over 6. These are all of our basic easy series we have. There are some more which could be classified as easy series, but they're not in this section, they're in later sections. Certainly read the test for divergence as many times as you need to, because it's very important that you never ever claim that the limit of a sub n goes to 0, therefore the series converges, because that's not true, because we have 1 over n sitting right there as a counterexample to that statement.